Okay, welcome everyone. Thank you very much for joining us today. So we have Maria Chiara Braidotti to present on the measurement of Penrose superradiance in a photon fluid.
Okay, I start. So hi everyone. Thank you for this kind invitation. It is a great pleasure to be here. So I'm going to present to you the recent measurements that we've made of Penrose superradiance in a photon fluid and the path that has led to this measurement. So this research project has been achieved thanks to a large collaboration of people, which I reported here. I don't know if you can see my mouse, and which I want to thank now, let's say not at the end. So let's start with a brief of, see if I can go ahead. Okay, the motivation behind this work. So I know that most of you, I mean, all of you at this point are part of a collaboration that works in this field. So I'll be, let's say, brief about it. So I'll start by introducing the motivation that led to these results. And so we know that some experiments, especially those related to the field of gravitational physics, aim at investigating effects that need a technology that is beyond our current possibilities. So in 1981, Unruh proposed a way to investigate these phenomena by extrapolating them from the gravitational context. And in particular, he proposed a dumb ball with a sonic horizon. So since then, there have been many platforms that have been used to investigate such phenomena. And many effects have been tested, or let's say, yes, many effects have been tested. I reported here just a few. The literature is very broad. It's more than 10 years. I think now it's 20, maybe more, that experiments are being performed. So I reported here a few examples of vacuum radiation experiments and superradiance. But there are also other fields that, like the one you're working in, so false vacuum decay, boson stars, Unruh effects, and many, many others. And so this work I'm presenting inserts in this, let's say, branch of physics. And so I'm aiming at describing superradiance from a rotating black hole in the field of nonlinear optics, and in particular in a superfluid regime. So let's start briefly with a small explanation on what is superradiance. So in 1969, Penrose proposed superradiance as a way for an alien society, actually, to extract energy from a rotating black hole. So his idea was that if an alien society could drop an object inside the ergosphere, the object could have inside the ergosphere a negative energy. So if the object inside the ergosphere splits into two, one part falls inside the black hole and the other part can be retrieved with more energy than the original object, because it acquires, let's say, it has lost, the original object loses a negative energy. So a similar but different, let's say, effect of amplification was proposed for waves in a different context in the same years, which is the Zeldovich effect. So in 1971, Zeldovich adapted the Penrose formalism to waves with angular momentum and noted that an observer in infinity can view any part of an incident rotating wave that becomes trapped inside the ergo region as having a negative energy. In this way, allowing for the amplification of the reflective positive energy counterpart. So from the point of view, start the video. So this is the way impinging on a, so the Zeldovich idea was based on a rotating cylinder, which was a metallic object. So from the point of view of the rotating object, the OEM wave undergoes a rotational Doppler shift. That is that the frequency of the incoming wave changes depending on the object rotation speed. So to see it visually. So this is what's happening in the reference frame of the rotating cylinder. And as soon as we increase the frequency of the cylinder, we see that the OAM changes sign, which is a signature of the, let's say, having a flip in the Doppler shift frequency. So if there, in this way, due to this flip, the reflected wave can acquire more energy than the original wave that it went in, because the absorption coefficient changes sign, becoming not more absorption, but actually gain. So the Penrose, in this way, this is like an analogy with what was the Penrose process for a black hole. So in the same years, let's say there was Meissner who fused the two ideas together, giving it the name for of superradiance to this amplification phenomenon. And we used the Zeldovich-Meissner condition, which is the one reported here, that gives us the condition for the amplification of waves with angular momentum. So the angular momentum here is m. Omega, the capital omega, is the frequency of the rotating body, so the black hole or the disk, while a small omega is the frequency of the incoming wave. So this phenomenon is difficult to study in astrophysics, and due to the enormous distances at play, but it's not, let's say, specific to the Zeldovich effect for conductors or to, let's say, the causing, which is the Penrose process for black holes. So, for example, it's also present in fluid mechanics, where it's known as, can be named as over-reflection. It has many names, or rotational superradiance. And as you all know, has been demonstrated experimentally by Silke here. Which this is the paper I'm citing here, and they showed the increase of the reflectivity when increasing the rotation speed, yes, of the vortex. So I'm going to introduce this now. So the scope of the experiment, instead, I'm presenting here, was to investigate further this phenomenon for fluids of light and exploiting the role of the negative frequencies that fall inside the hole. So I'm going to briefly present what is yes, a photon fluid. So let's start from scratch. I don't know how many of you know about it, so I'll start from the beginning, trying to be fast but precise. So in optics, the equation that we use to describe the nonlinear regime is the nonlinear Schrödinger equation, which is this one, where E is the electric field of light. We can see that the 2D NLS has a derivative in the propagation direction and a derivative in the transverse dimension, which gives us the diffraction. Then there is the nonlinear term that takes into account the nonlinear variation of the refractive index proportional to the optical intensity of the field. So we can write this equation in this general form with a non-local expression for the refractive index, which is, let's say, the integral of the non-locality function, response function, with the square modulus of the field. This means that the refractive index in a certain point of the sample is affected by the value of the beam in a place close to it. I wrote here the solution of this equation in the general form, but we are gonna look at this field inside here. So the field below is the one inside. The vector here, E, small e, is the polarization, and this is the, let's say, carrier wave. So we know that this equation describes the thermo-optic light-matter interaction. So if we send a strong pump and a weak signal inside the sample that has this nonlinearity, we can have a process which is called four-wave mixing, which will generate a weak idler beam. And the basic physical process here behind is that two pump photons combine with one signal photon to create the idler photon. And this four-wave mixing process, let's say, can produce an amplification of the signal and the idler fields when with, let's say, the required power coming from that of the pump. So the amplification, to have amplification, we need phase matching. And the phase matching requires the interaction between the signal and the idler to be phase synchronized. So this four-wave mixing process is the means by which we are going to, let's say, have an incident particle that then becomes split into two parts as needed for the Penrose process. And so I'm going to describe now how the thermo-optic system can be seen as a photon fluid, so with a complete notion of Bogoliubov excitations with respect to the strong pump. So everything will be in the reference frame of the pump. Let's say, so this carrier wave will be removed. And the power of this approach is that these Bogoliubov excitations that are the one that serve as quasi-particles in the quasi-particles that participate in the Penrose process. So let's look a bit now at the thermal nonlinearity. So the particular thermal optic medium we used in the experiment is composed by a solution of methanol and a low concentration with a low concentration of graphene nanoflakes. This graphene provides a weak absorption of the pump input beam that enhances the thermo-optic effect with a nonlinear coefficient gamma, which was N2 in the other slide, that is negative, which means that we have a defocusing nonlinearity. Specifically, the non-local response may be written as a zero-order modified Bessel function. And this is a very versatile setup because by performing measurements which are time gates, so we have a time evolution, which is different from the Z evolution in time, in space, let's say, of the beam. So actually the real time of the experiment. And by taking measurements over a short time, which is like 0.2 seconds in our case, it is possible to have a strong nonlinearity, but with a very weak non-locality. So like 200 microns. And since the thermal diffusion has not had the time to develop, so the steady state to reach the thermal, let's say the thermal steady state is around 20 seconds. So an order of 2 orders of magnitude higher. So as long as the beam involves dimensions that are larger than sigma, the nonlinearity can be is highly to a highly degree local. So let's go back to the photon fluid. So from the NSC, which is the first equation, it's possible to describe the photon fluid. By doing the modein transformation, we can map the NSC into the two hydrodynamics equation for the intensity rho of the field and the phase. So we have the continuity equation for the intensity and the Euler equation for the phase. And if we have a spatially homogeneous photon fluid where the background, so pump, is independent of the position R, so the transverse position, we can have a sound mode of the form of a plane wave with a wave vector K and an amplitude which is proportional to the signal and idler amplitudes. So the signal and idler now are a perturbation on top of the pump background, which is the one responsible for creating the nonlinear background. And so we have this wave vector K, and we have an angle, a frequency of these beams, which I call capital omega here. And for these modes respond to to have this dispersion relation, which is the dispersion relation for the Bogoliubov modes, which is composed by two terms, one that is linear. So let's say the first one, which is proportional to this, let's say all these constants made up the speed of sound, and a quadratic term. So the fluids in our case lives in a 2D space. So the axis Z, that was Z here along the propagation, actually maps into time. So at different slices of the sample, we have different instants of the propagation of the fluid. So I reported here a measurement of the dispersion relation, but actually it has been also done by a group, Glorier group in France, with a more effective technique that I discovered a few years ago, which is this one that I briefly reported for you if you want to check it. But now let's going back. So until now, I spoke about a constant background on top of which we put our mode, our perturbation. But actually, to have a rotating space-time geometry, we need an inhomogeneous background. So to test the Penrose process, we introduce inhomogeneities in the pump beam, and inhomogeneities can create an effect, actually not can, they create it all the time, an effective curved space-time where the linear elementary excitations can propagate. So by perturbative analysis of the hydrodynamics equations I showed you before, it is possible to show that in the limit of linear dispersion, so when we have the supersonic flow, the dynamics of the perturbation can be described by Klein-Gordon equation in a 2D plus 1 space-time with a certain metric. So let us keep in mind that the velocity here that we see V0 is proportional to the gradient of the phase of the beam. And hence it can be engineered very easily in different forms. So the characteristic space-time that we need has, let's say, need to have an ergo region, which this has, where these quasi particles can have negative energies. This allows us to extract energy from the vacuum and to amplify the waves in a classical scattering process. So this is the key ingredient for having superradiance. The role of the horizon in this context is more subtle and is essentially act as a one-way membrane. So it has to prevent the mixing at infinity of the negative and the positive mode. I briefly report here a citation where I saw a paper that reports the first, I mean, for us at least, engineering of a black hole. So what we create, what we have is an OEM beam, large OEM beam, which is the pump background, which has, where we can measure the speed of sound and the flow as well, the derivative of the phase. And in this way, we engineer, let's say, the black hole with its ergo region, and we want to send into it the signal and the idler that are the beams that we want to amplify, and that have to, to behave as the positive and negative norm modes in the Penrose process. So let's go back to the full fields description, so to the signal and idler and pump beam. I report here the linearized propagation equations for the perturbation, which so the perturbation, as I was telling you, is composed by the signal and the idler, that for us form together the Bogoliubov excitation. So the strength of these results is that it lies in the versatility, in the validity beyond the acoustic approximation, which we no longer need to monitor throughout the scattering in order to trust the results. And I'll show you later how. So our superradiance results for a wave packet propagation hold over the entire Bogoliubov spectrum. And the price we pay for doing this is that we need to measure both the positive and negative modes. So they both need to be measured in the analysis. So we are looking for here for a geometry where we want to identify which are the positive frequency modes that are amplified and which are the negative frequency modes that are trapped. So the geometry we found is this one. We have a background pump, which is an OEM beam. So all the quantities here are translated into the pump reference frame, as I was telling you before. So we have a background pump, which is fixed as much as possible, that propagates inside the nonlinear sample and creates the background. then on top of it, we have the input signal. And the signal is another OAM beam, which is, let's say, starts larger, so outside the pump core, and shrinks onto the pump core. So when it focuses at the focal point, we have, let's say, the most of the interaction between the two beams because they become phase matched. So from that point on, so from that point in that region, we fulfill the phase matching of the beams, so we can create the idler. So the aim is to couple them in a way that they create an idler, which is for us, has to behave as the negative negative frequency mode, and that remains trapped inside the ergo region of the pump, so inside the core, let's say. I'm identifying the ergo region with the core. They're slightly different, but please, let's leave it this way. So the idea is that at the end, we want to see, we have 3 beams which we can detect, which are the pump, the output signal, and the generated idler. And they have to be spatially distributed in a very precise way. So this way, this nonlinear effect, let's say, phenomena is thanks to the Penrose process, we actually are able to find a new type of phase matching, which is geometrically induced. So we have the phase matching by the geometry of the beams, and the region where they're phase matched is near the focus, as I was telling you before. So let's look at now at the wave vectors with respect to the pump of the signal and idler beams. How do they look like? So for the signal, we have that it's composed by 2 terms. One is the, let's say, nonlinear wave vector that is usually there. And then there is this bit here where gamma is the penetration of the signal inside the pump core. So it's an overlap integral of the signal interacting with the core. While for the idler, we find out that there is this beta, of course, as always, plus this eigenvalue mode of the guided mode. So what this means? It means that the core is creating like a sort of waveguide. So it has since it has a lower intensity, it creates a guiding potential, and this guiding potential is what acts as an event horizon, because it prevents the mode that it's inside to go out. So what we need here is, and the thingy here is that we have the trapping only if this lambda coefficient is larger than 0, sorry, so it's positive. And this translates in the beam in having a negative frequency. I'm going to show you it in a couple of slides. So we find this phase matching condition. So since it's, let's say it's not strictly speaking, it's not a crystal, so we don't have it equal to 0. And since they are not, they have an angle at which they are propagating, the phase matching condition is not that delta K has to be equal to 0, but since the beam are focusing, it has to be greater than 0. And this phase matching guarantees the excitation of the idler inside the core, and hence also the amplification of the signal beam. So if we look at, translate everything, sorry, I went too far, into the frequencies. So we can map the K vectors into frequencies by this transformation here. And we find the frequency nonlinear shift. So the frequency nonlinear shift is composed by the shift of the signal plus the shift of the idler. And by, let's say, putting it mathematically, we find the same condition as the Zoldovich-Misner condition. So our phase matching condition is exactly the Zoldovich-Misner condition we were having for Penrose-Superradiance, where omega, so the small omega here, this one, is an average of the frequency of the signal and idler. So it's the average frequency of the Bogoliubov mode. And capital omega is the frequency of the rotating vortex, which is proportional to the difference in OEM of the pump and the signal beam. So since this has to be positive, this leads to a condition onto the OEMs. So we have that the OEM of the signal has to be larger than the OEM of the pump. And plus, due to the trapping I was showing you before, sorry, delta K has to be positive because of lambda had to be positive in order to have the trapping, which translates that if we have trapping, we have a negative frequency of the idler. So the idler behaves of the negative frequency mode, while the signal is the positive one. So just to summarize, these are the three conditions that we numerically tested, but also then had to verify experimentally. So we have a condition for the OEM, a condition for the idler mode in order to have the trapping, and the phase matching condition. So if the three of them are verified, then we can have the superradiance phenomenon. So the tool that we use to say that we have superradiance is this nether charge conservation. So if we look at the original equations, we find out that they conserve this quantity. And this quantity is proportional to the intensity of the signal minus the intensity of the idler. So what's happening here is that you see that now the idler is the negative norm mode, and it just appears from the conservation of the charge. And this allows us to define a reflection and transmission coefficient. So the reflection coefficient is the charge, let's say the integral on the current, which is this bit inside. So J is the current, the whole together is the charge. And outside the scattering region, which we call ROV, so it's the ergo region. It's all happens in that near the focal plane, while the transmission coefficient is the remaining integral inside. Since this is conserved, so the sum of the two has to be conserved, and the sum of the two is actually the nether charge. So these are simulations. So in the simulations, what we did, we took a pump with OEM1, and we make it propagate. We put on top of it the signal, and we vary the OEM condition, the OEM of the signal in order to satisfy the OEM condition and in order not to satisfy it. So in the first row, we have an n equal 2, so OEM of the signal equal 2, that satisfies the condition. And we see this is the propagation axis, and we see that the beams, let's say, start interacting near the focus, and then they keep interacting also after. And we see that the reflectivity after the focal plane becomes larger than 1. And this is the sign of having, let's say, amplification. While in the case where we do not satisfy the OEM condition, the reflectivity is always below 1 or 1. So we have no amplification of the signal. Or I would say no amplification of the positive mode. So how did we do this experimentally? So the experiment is, the setup is this. So we engineered two beams, the pump and the signal, with their phase profile and intensity profile, which I report here. So this is the intensity of the pump and of the signal. I reported so the pump, we changed it with two OEMs, L equal 1 and 2, and the signal with various OEM. So this is an example. These are two examples. We let them propagate in this thermal nonlinear medium that I was telling you before. Oh, sorry. Oh, come on. Okay. And we image the output. So we do not have access inside the material, but we can image the output. And at the output, we are able to have, through this interference technique, to both measure the intensity and the phase of the whole field outside. So once we measure the intensity of the phase, and the intensity and the phase of the beam, we can do a Laguerre-Gauss decomposition and to see which are the beams that are actually present in our field. So if we have a linear measurement, we have to see just the pump and the signal. There has to be no creation of the idler. And we verified this here. So here the idler should be here, and while in the first case it should be at OEM equals 0. And while in the nonlinear measurement, we expect to see the creation of the idler if we are phase meshed. So only if we satisfy the superradiance condition. So only in the first case. So we still do not have to see the idler, which is here. This is actually that's true. In the case of non-phase matched situation, let's say. So after we do the Laguerre-Gauss decompositions, we have our experimental fields that we can reconstruct mathematically, and these are the measured ones, which result very clean because after you do the decomposition, you basically remove all the noise. It's just the transformation. And we plot the currents. And we see that when we satisfy the phase matching, so when we have superradiance, we have a negative current. A negative current is the sign that we have a transmission mode. So a mode that has been transmitted inside the ergo region. If we think of the integral before, it means that the transmission integral is different from 0. So that we have an idler. While if we do not have this negative current here, so like in this case here, we do not have the idler, which means that there is no superradiance. We can also see from the reconstructed fields here that when we have superradiance, the field, the idler is all trapped inside the ergo region. So most of it at least, while the signal is outside. While in the other case, that is not the case. Plus, I've not reported the scale here, but if you look, so it seems they are all the same colors, but if you look at the scale of the intensity of the idler beam, in this case here, it's very weak because it's not phase matched. So it's there, but it's very, very weak, like a really small percentage. And after the currents, what we do is we measure the reflectivity. So we're able to measure the reflectivity. And what we see is that when we are for the OEMs, so these are plots for different OEMs and of the signal and hence different OEM of the idler. When we satisfy the superradiance conditions, so let's say when we are positive with and when M is positive, we have that there is an amplification. Actually, also this point here is above noise and above 0, but it cannot be seen in this scale. It's like an amplification of a few percentage, 0 point something, but it's significantly above. While every time we do not satisfy the condition, we see that there is a stronger absorption and say the reflectivity is below 1. And same case with the pump OEM n equal 2. We have absorption when we do not have superradiance, so when we do not have phase matching, and while we have superradiance when we have phase matching. So I don't know if I have a few more minutes. Okay, so because this is let's say what I had to say about this project, but actually if I have a few minutes, I wanted to talk to you also about another project we have been carried out, which is related because it's still amplification in rotational amplification. So it's a theoretical proposal of seeing the Zeldovich effect with rotating spheres. So as I was telling you, the Zeldovich effect, okay, I do not explain again what is the Zeldovich effect. I think you all know at this point. So we have an inversion of the absorption coefficient when the Doppler shift frequency gets negative. And what we noticed is that most of the literature is that tries to investigate this phenomenon in the far field, while we actually think that the near field is the key in order to observe the Zeldovich effect. So near field means that the frequency of the wave is much larger than the dimension of the rotating object, but you have an interaction between the object and the wave. So these are a few examples of where we are now with technology and where we should be in order to see the phenomenon. So we are very far from, let's say, do this in the far field, but we could try to see it in the near field. So this is, let's say, the literature behind it, but there is actually much more. So it has been investigated widely. So our calculation do not have a cylinder anymore, but I have a sphere. So it all started from actually a paper on, they had this paper, which is actually a very nice, very cool paper. So they had these spheres that they were magnetically levitating them and spinning them, and they were making them explode with the rotation. So they were increasing the frequency of the rotation of the sphere, and then studying how did it break. So we saw this paper, and it came up it could be adapted to test the Zeldovich effect. So this system is made like this. So this is our proposed setup. We have 4 microcoils. These microcoils are linked through transmission lines. So in the transmission lines, in such a way that the field that they generate inside is shifted, and in this sense, it has an OEM. If we think of L as the total length of the whole transmission line, so of the four bits, L is the frequency of the field. So we have just like a mode inside this circuit, okay, that is rotating there and generating an evanescence field inside the cavity. So what's happening is this, as the current goes inside and does its path, the B field inside rotates with an OEM and a phase. So what happens if we put now the sphere inside it? A metallic sphere feels, of course, the presence of this magnetic field in this way. So we can we excite momentum M, which is proportional to the field. Alpha is the interaction that is given by, it's with respect to the, it's called slip frequency. So it's the frequency difference between the frequency of the field and the frequency of the rotation. So small omega is the frequency of the B field, while capital omega is the frequency of the rotation of the sphere. And this has 2 components, one that is, let's say, real and one that is imaginary, but let's say we can write it this way, one that is in phase and one that is out of phase. When we, so we have a non-Zeldovich situation, so when the field spins faster, so its frequency is faster than the rotation of the object, we have a delay. So the moment the M here follows the field with a certain lag, and the lag is given by the response of the current of on the sphere. While if we have a Zeldovich effect on the other hand, what happens is that you flip the out of space part in a way that M now precedes the B field and leads to an amplification. So mathematically what is happening is there. A is the vector potential. So this is the equation for the vector potential of the field. with some boundary condition at the edges of the sphere. J is the current, the density, actually, density current inside. So what you see here is the density current inside the sphere when it is rotating. And we can see that if we want to calculate, we can calculate the power dissipated by the sphere of the field, and we see that it's proportional to what is called K, actually, and this was A in the previous slide. And it's with respect to omega r, which is this slip frequency, so the difference of frequencies. When this becomes negative, what happens is that this changes sign. So the power dissipated by the sphere becomes the power that is actually amplified by the sphere. And we can see that, so if we want to plot A as the loss factor, this loss factor now becomes an amplification. Okay, so the sign depends on the difference of the frequencies, where, let's say, L0 and L, so L0 is the length, actually is the impedance of the transmission line, while L is the impedance of the 4 coils. And if we plot A for various frequency, both let's say changing the frequency of rotation of the sphere and the frequency of the field, we see that we have a region where we have gain and a region, of course, where we have losses. So they are divided here. And if we take a line here, we see that there is, let's say, absorption up until the frequency of the sphere is larger than the frequency of rotation of the field. So we flip the sign of the absorption. So A is the absorption. So when it goes negative, it means we have gain. And so this was a theoretical proposal. Of course, it has, I mean, it's at the edge of current technologies because we need a very long transmission line. And which is, it can be done, but it's still very challenging. So they are not commercialized, for example. And of course, the transmission line has to be superconductive. So all of these has to be very cold. And so there are some critical points. Some of them are also the mechanical stability of the rotation, and yes, the super long circuit. So it requires a 70-meter circuit, so it's fairly long, but still doable. But the nice thing of this is that if we could actually, by reducing the temperature and reducing the, in order to remove the thermal states, it could be possible to try to make this quantum. Of course, it's very far for the moment, but it could be a further step of these kind of setups. And this would not be testing the analog. This could be a test of the actual effect. So that's the interesting bit. And so I stop here, and I thank you all for the attention.
Thank you, Maria, for your nice presentation.